Hello everyone, welcome to lecture on microprocessor systems and interfacing. My name is Dr. Vilayat Khan. I am an assistant professor at Comsets University, Islamabad campus. These slides have been edited from different sources, including the two sources given here. The topic that I'm going to talk about in this lecture is interfacing memory with 8086 and 8088 microprocessors. 8086 and 8088 are one of the most popular microprocessors, in fact all the microprocessors. So the memory interfacing would be discussed by giving examples of memory interfacing with 8086 and 8088 microprocessors. Here we have a block diagram of the 8086 microprocessor interfaced with memory, input and output devices, and this microprocessor is working in the minimum mode. So when the 8086 microprocessor is working in the minimum mode, the basic control signals are directly available from within the microprocessor. Here we have the CPU 8086 microprocessor, and it is connected with an external clock generator, 8284A clock generator. The three outputs of the clock generator, clock, which provides the basic clock signal to the microprocessor, ready and reset outputs of the clock generator are connected with the three pins, clock, ready and reset of the microprocessor. The control signals are generated by the microprocessor, input and output, or memory control signal, read signal, write signal, interrupt, acknowledge, data transmit and receive, data address enable, address latch enable, and so on. The minimum mode of the operation can be selected by connecting the maximum mode pin with the VCC, which is logic 1. So this will select the microprocessor to operate in the minimum mode. The address and data multiplexed pins are connected with latches to demultiplex address and data from each other, and this would give us the address bus. So externally the latches are connected with the address bus, and similarly the address and data multiplexed pins of the microprocessor are connected with the bidirectional transceivers, and the direction of this bidirectional transceiver is controlled with the data transmit and receive pin. And the data transmit and receive pin will decide if the data is going outside of the microprocessor or it is coming inside of the microprocessor. The direction is related to the operation, if the data is being written to the memory or it is read from the memory. There is an interrupt controller as well that receives interrupt requests from external devices, and this interrupt controller is then generating an interrupt request that is sent to the microprocessor through the interrupt request pin. When this microprocessor receives the interrupt request, and if the interrupts are enabled, then it would call an interrupt service routine or interrupt handler, and that will be executed to respond or to address the interrupt request that has been received. So this microprocessor is connected with or interfaced with random access memory, which is connected to the data bus, address bus, and some of the control signals. Similarly, read-only memory is also connected with the bus of the microprocessor, and input and output devices are also connected with the buses of the microprocessor. So if the 8086 is working in the maximum mode, then the interface with external world would look like this. So it's connected with the clock generator, and there is a bus controller called 8286, 8288 bus controller. So this bus controller is responsible to generate some of the control signals. So this bus controller is connected with the three status pins of the microprocessor, and in response to 8 possible values of these three status pins, this bus controller generates control signals, and those control signals are more specific. In case of the maximum mode, the separate lines of, for example, or for memory and input and output operations are generated. So These separate control signals are different for memory and input and output operations, while in case of the minimum mode, normally the control signals are common. So for example, for the memory read, there is a memory read command and memory write command, while for the input and output, there is an IO read command and IO write command. So the data and address fins, multiplexed address and data fins are demultiplexed like before. So there are latches which are demultiplexing the address and data from each other, and there is a transceiver that is buffering as well as controlling the direction of data flow. And there is an interrupt controller, RAM, ROM, and external input and output devices are also connected with the bus. So memory system is there. So simplex or complex, every microprocessor system has a memory system. So to store data and instructions. So data and instructions are then brought to the microprocessor registers, and which are executed then one by one. So almost all systems contain two types of memory called read-only memory or ROM, and random access memory or called RAM. So read-only memory then in turn has different types. The first type, which is that is called the ROM, is read-only memory, and this type of memory can only be read while it cannot be written to. So this type of memory is manufactured with data written to it, and the data cannot be modified later on. And this kind of memory is also called non-volatile memory, because even if the power is shut down, it will still retain the data. Then later on, a programmable version of the read-only memory was also introduced called programmable ROM or PROM. This type of memory is not very commonly used. In programmable read-only memory, the data may be written later on using ROM programmer. And then there is an EEPROM, which means that erasable programmable read-only memory. So it's the kind of memory that can not only be read but can also be written to it later on in the field. And then there is a latest type of ROM that's called EEPROM, that means electrically erasable programmable read-only memory. So this type of memory is also called flash memory. So this type of memory can be many times modified or written to it in addition to reading data from it. So this kind of memory is normally used for storing the basic input and output operating system called BIOS. In many systems, random access memory is a kind of memory that is volatile. So if the power is not present, then the data on the memory would disappear. There are two types of random access memory: static random access memory and the static random access memory doesn't require any additional circuitry to retain the data when the power is on. And the other memory called dynamic random access memory requires some refresh circuitry to refresh the data written to it over a certain interval. These random access memory is comparatively used in small quantity in computer systems, and it is comparatively faster. And normally ROM is used to store basic operating systems in the system, and it is normally used when the data is to be retained even if the power is shut down, while random access memory is used to provide faster access to the data and instructions when required by the system. The memory, to access the memory, the address generated by the microprocessor needs to be properly decoded, and for that purpose certain types of address decoder are used, and one of the most popular address decoder is 74LS138. This is a decoder with 3 enable inputs. So this is basically a 3 to 8 lines decoder. So here in this decoder there are 3 select inputs represented with A, B, and C, and these 3 select inputs would choose or select either of the 8 outputs, and the other 3 inputs are basically the enable inputs, designated with G2A, G2B. These two input enable inputs are low active, while the G1 is high active. So to enable this decoder, the G2A and G2B input must be 0, while G1 must be 1, so that this decoder is enabled. And when this decoder is enabled, these three input lines or select lines will select either of the 8 outputs. So for example, here we have the characteristic or truth table of this decoder. So when G2A is 1, G2A is 1, then regardless of the other inputs, all of the outputs would be 1. And when G2B is 1, then regardless of the other inputs, all of the outputs would be 1 as shown here. And when G1 is 0, then regardless of the other inputs, all of the outputs would be 1. But when G2A and G2B both are zeros and G1 is 1, then the inputs at these three select inputs would determine which output is 0. So for example, if all of the selection inputs are zeros, A, B, and C are zeros, then the first output, which is output 0, would be 0. When 0, 0, 1 is provided, the next output, which is output 1, would be 0. And as shown in this diagonal, all the 8 possibilities of the input at these three lines would choose either of the 8 outputs to be 0, while the rest of outputs would be 1. Here we have a typical memory device. This is a representation of all the memory devices, whether they are RAM or ROM. In each type of memory, there is a set of address connections. Here we have address connections, and these address connections or fins are designated with A0, A1, A2, and AN, depending on the number of address fins in the memory unit. And on the other side, we have the output connections or the output pins. These output pins are designated with O0, O1, O2, and ON, depending on the number of outputs that can be taken at one time from this memory unit. These output pins may be used just for sending the data output, or may be used for input or output connection both. In addition to these input fins and output fins, there are some control fins as well. One type of control pin is the write enable, that enables the write operation onto this memory chip, and that is designated with normally WE, and this is active low in this case. And in addition to write enable, if when the memory unit is to be read for that, the output enable should be used, so that the output is enabled, and that is designated with OE, output enable. And this operation is normally called reading operation. So whenever this memory chip is to be read, then read should be sent as 0, so that this would enable the output of this chip. So output data may be read from these output pins. And for either of these operations, the chip may be selected, so that that is chip select. So there is a select line which is also active low in this case, and when A0 is provided through this pin, this chip is enabled. And when this is enabled, after that reading or writing operation can be performed on this chip. When this chip is not selected, even if the address is provided, the reading or writing operation will not happen. So to read or write from or to a particular location inside this memory, this chip first be selected, and then the output enable or the write enable would choose the desired operation, whether it is reading or writing. And after the desired operation is selected, the data would be written to this memory chip or read from this memory chip through these output lines. So the number of address pins is here on this chip is directly related to the number of addressable locations in the memory chip. So the more addressable locations available in this memory chip, the more would be the number of address pins on this chip. And the number of output pins on the chip depends upon the address, the data bus connected to this chip. For example, and also the number of bits that can be stored at each location of the memory. For example, if each location here has the capacity of storing 8-bit, then there will be 8 output pins, so that 8-bit data may be read or written at each location. The number of pins and as I said, the number of pins and the number of locations inside the memory chip are directly related to each other. So for example, if the memory chip has 1 kilo locations, and that 1 kilo location in the binary means 1024 in the decimal. So for 1024 locations, we need 10 bits in the and 10 bits, and 10 bits 2 raised to power 10 in the binary system is equivalent to 1024. So for 1 kilo addressable locations, we need 10 bits of address so that each location is uniquely addressed. So if, for example, this memory chip has 1024 memory locations, then the address pins would be 10 here, and those address pin would be A0 till A9. And if the memory locations are double to that of the 1 kilo, so that would mean that we have 2048 memory locations. And for that, to uniquely address them, we need 11 bits, and so on and so forth. And finally there, for example, for the 512, we need 19 bits. For 1 mega locations, we need 20 bits. And for 2 mega locations, we need 21 bits. So increasing the address, increasing the address by 1 bit. So if this address is increased by 1 bit, it doubles the number of addressable locations. We would be able to address double addressable addresses or double addressable locations inside the memory. Here we have an example. It's the pin out of the EEPROM 2716. This 2716, the chip ID. So this chip has 11 address inputs and 8 data outputs. And that means that the organization of this memory is 2 kilo cross 8. 2 kilo is the number of addressable locations inside this memory chip, and 8 is the capacity of each location. So 8-bit data can be stored at each location. So to address 2 kilo locations, we need 11 address inputs. So there are 11 pins, and they are designated with A0 till A10. So these are the addresses, and as each location stores 8 bits, so 8 are the number of output pins. So O0 till O7 are the pin numbers. And then there is a chip select here, chip select that would enable this chip. And then there is an output enable pin, also designated with program or power down pin, PD or PGM. So power down or program pin. This works as a output enable pin. So whenever the data is to be read from this pin, a 1 should be provided here, and to enable this chip, a 0 should be provided here. So here we have some examples of how different amount of memory, RAM and ROM, can be interfaced with the 8086 and 8088 microprocessor. So here in this example, we are using a very simple NAND decoder to decode the 20-bit address from 8086 or 8088 microprocessor. And the memory chip used is 2716, and the organization of this memory chip is 2K cross 8. So that means there are 2 kilo locations inside this memory chip, and each location can store 8 bits of data. So obviously we need O0 till O7 are the output pins, and to address each location of the memory for 2 kilo, we need 11 address pins. So A0 till A10 are the address pins, and then there is a chip select pin that enables this memory chip. So this is a 2 kilobyte memory in total, and we want to interface this 2 kilobyte memory with the with 8086 or 8088 microprocessor. So remember that in these microprocessors, the address is 20-bit address. So we need to decode the 20-bit address in such a way that that only the locations are properly addressed inside this chip. So 2 kilo locations are valid addresses, and those 2 kilo addresses should be properly decoded so that each address identify a location inside this memory chip. So for that, out of the 20-bit address coming from the microprocessor, the first 11 bits are chosen to address a location inside this memory chip. So as there are 2 kilo locations, so 11 bits are sufficient to address each location separately. So 11 bits of the address is coming towards this chip. So these 11 bits would uniquely identify a location inside this chip. and then the rest of bits from A11 till A19 are connected to a multi-input NAND gate. So all these bits should be 1, and then to this multi-input NAND gate, the IOM pin is the inverted form of IOM pin is connected with this multi-input NAND gate. So for example, as this input should be 0 here, because IOM prime means that as we are accessing a memory, so in case of memory access, the value of this pin should be, which is a microprocessor pin, should be 0, and this 0 is inverted, so we get 1 here. So all of the inputs are 1 here. When we want to access this memory unit, all of the inputs here are 1, and we would get 0 here. So we get 0 here, and this is an OR circuit. And at this moment, the read signal or the memory read command signal coming from the microprocessor is also 0. So 0 and 0. So you will get 0 here, and as this chip select is a low active, so this chip would be selected, this chip would be enabled, and then whatever the address is provided at these 11 lines, they will select a memory location, and from that memory location 8-bit data would be put onto the data bus, and that would complete the read operation. So this is, we are using a simple NAND decoder to interface 2 kilobytes of ROM with the microprocessor. So this is how a 20-bit address is decoded here, and how the data bus is connected with the output pins of the 2716 memory chip. So this is 2 kilobyte ROM interfaced with microprocessor, and if we want to double the capacity of this ROM, then we can add another chip with this chip, and then accordingly, of course, the number of addresses, valid addresses, here are 2 kilo valid addresses, and when we add another chip of this kind, then the number of valid addresses would be doubled. So accordingly, we would need to decode the 20-bit address, so that double of 4 kilo addresses out of the 1 mega addresses, which are the total capacity of addresses for the 20-bit address. So out of 1 mega addresses, we need to only decode the 4 kilo addresses. So that would look like this. Okay, so this is what I just explained, and here we need also to calculate the valid addresses. So for the valid addresses, as I just said, as 0 till at 10, these lines, the value of these lines would change from all zeros till all ones, while the other bits A11 till A19 must always be 1. So to address the first location inside this memory chip, all of these bits should be all zeros, which are shown here. Okay, so this would provide the starting address, and if we represent this value in the form of hexadecimal digits, then F, A16 till A19 are all 1, so this would give us 1F, and A12 to A15 are all 1, so that would give us another F, and 100 would give us another hexadecimal digit, that is 8, and A0 till A7 would give us 2 other hexadecimal digits, which are 00H. So this FF800H is the first address, valid address of 20-bit valid address that would land or identify the first location inside this memory chip. And to calculate the last address in this chip, the A11 till A19 must always be 1 to get a 0 here, so that this chip is selected, while the other 11 bits should also be all 1s, so that it would give us when A0 till A7 all bits are 1, so then this would give us the final address inside this chip. So when we represent this value in as hexadecimal digits, then you would get FFFH. So this is the last address, valid address inside this memory chip. So when a 20-bit address is provided, this 20-bit address is decoded as Okay, so when a 20-bit address is received, this 20-bit address is decoded as here. So the first address inside this chip is FF800H, and the last address is all Fs. Okay, so if we want to double the capacity of the memory, so we would need to attach another memory chip, 2716 EEPROM. So as each chip provides 2 kilobytes of memory, and if we attach another chip, then we would get double the memory capacity, and that is 4 kilobytes. So accordingly, the number of valid addresses are now doubled. So we need to decode the 20-bit address as here. So 1 bit is taken from here, and instead that is used here. So that is A11. So A11 is used with an inverter, and before the inverter it is connected with the first chip, and after the inverter it is connected with the second chip. So the same A0 till A10, these address lines are connected with both of the chips. They are connected here, they are connected here, and the 8-bit data bus is connected with the output pins of both the microprocessor. So it's the same bus but represented with 2 arrows. But it's the same bus, 8-bit bus. Okay, so when A11, the rest of calculations is the same as before, but when A11 is 0, we get 0 here, and this chip is selected. When A11 is 0, we would get 1 here, and this chip is not selected. But when A11 is 1, then the first chip is not selected, and A11 is 1, so we would get 0 here. So the second chip is selected. So depending on the value of A11, if it is 0, this upper chip is selected, and when A11 is 1, this second memory chip is selected. So in either of the case, the address is provided as usual, only this bit is changed to get the byte from, to access the byte from either of the 2 chips. So both of the chips are now available to read data from them, and we would get a total capacity 2 kilobyte here and 2 kilobyte from here. So we would get a total capacity of the memory would be 4 kilobyte. In some memory chips, as we saw a typical memory unit, there may be an output enable pin in addition to the chip select. So in that case, if the chip has an output enable pin, then the read signal is connected to that output enable pin. Similarly, if we want to interface an 8088 microprocessor with the 64 kilobyte ROM, then we can use multiple memory chips for that purpose. For example, we have 2764 is a memory EEPROM chip, and this chip is 8 kilobyte. So there are 8 kilo locations inside this chip, and each location can store 8 bit of data. So the total capacity of each single chip is 8 kilobyte, and if we combine 8 chips like that, we would get 64 kilobyte of total memory capacity. So to do that, every chip has a chip select pin that is low active, and as there are 8 kilo locations inside each chip, so for that 13 bits are sufficient to address each location inside each chip. So these 13 address lines are connected with every chip in this array, and similarly each of these chips has 8-bit capacity in every location. So every chip has 8 output pins, and these 8 output pins are connected to the 8-bit data bus lines. So if a data is to be read from either of these chips, that data would be read through these 8-bit data bus. And similarly, to identify or to locate a location inside either of these chips, then the 13-bit address is sent to all of these chips. But the select line would choose or select one chip among these 8 chips at a time, and this is done through a 74LS138 decoder. So this decoder is a 3 to 8 lines decoder, and this decoder has 3 select lines or enable lines. So G2A and G2B should be 0 to enable this, while G1 should be 1. So out of the 20-bit address coming from the microprocessor, the 13 bits from A0 till A12 are provided or connected to the address pins of these chips. So 13 bits are connected there, and then the rest of the bits A13, A14 are connected to the select lines of this decoder. A0 till A12 are connected with the address pins of these microprocessor. A13, A14, and A15 are connected with select lines of this decoder. And A16 till A19 are connected with the enable pins of the decoder. So A16 is connected with G1, and these three lines are address lines are connected with G2B through an AND gate. To enable this chip, G1 must always be 1, G2B must always be 0. So to get G2B 0, these S17 and A18 and A19 must be 1, so that we would get a 0 here, as we are using a NAND gate, so you would get 0 here. So to enable this decoder, S16, S17, A18, A19 must always be 1. These three lines, the value of these three lines should change, so that for all zeros we would get 0 at this 0 output. For 001 we would get 0 at this output, and so on and so forth. So for all these three inputs, there are total 8 possible input values, and for every value we would get one of the 8 outputs 0, and all of the rest would be 1. So the 13-bit address coming here would choose allocation or identify allocation in each of these 8 chips, and these 3 lines would make one of these outputs as 0, and each of the output is connected through an OR gate, which is taking another input from the read signal and is connected to the chip select input pin of each pin. So for example, the 13-bit address here would identify allocation inside all of these chips, and let's suppose S00 is provided here. So that would make this line 0, and if the microprocessor is performing a read operation, then obviously this memory system would get a 0 from the read signal here. So 0, 0 is received here, so a 0 is received here, and this would enable the first chip, while the rest of chips would get 1 here. Why? Because 0 is provided here, so only this line is 0, while all of these lines are 1. So all of these chip select pins would get 1 here, and as they are low enabled, so all of the rest of chips would be disabled, they would not be enabled, and only the first chip would be enabled. So the write or the read operation would happen from the first chip only. So the 13-bit would identify a location inside this chip, and from that location the 8-bit data would be read. In this memory system, when 64 kilobytes of memory is interfaced with the microprocessor, the first address begins at F000, because these 4 bits are always 1, while the rest of bits are changing, and the last address would be FFFF. So this is the first address, and this is the last address of this entire 64 kilobyte of memory. And similarly, for each memory chip, the address range is F0000 as the first address or first byte inside this memory chip, and F1FFF as the last byte inside this chip. And these are 8 kilo locations range, and each of this address is inside this range. And then the next range begins for the next chip, and that is F200 is the first address inside the second chip, and F3FF is the last address inside that chip. And similarly for other memory chips, there is an address space. So this total memory is 64 kilobyte, even though there are 8 memory chips, but for the microprocessor, the group of all these memory chips looks or appears as a single memory chip with 64 kilobyte or 64 kilo location or 64 kilobyte total read-only memory. Similarly, there is another example, 8088 interfacing with 512 kilobyte RAM. So in this memory interfacing example, there is an 62256 memory chip with the capacity of 32 kilo locations inside each chip. So every single chip has the capacity of 32 kilobyte, 32 kilo are the locations inside this chip. So 15 bits are sufficient to identify a location inside each chip. And then there is an array of 8 chips. So this would give us 256 total capacity, 256 kilobyte of total capacity. And then there is a similar another group of memory chips, and this would give us another 256 kilobyte of memory. So 256 kilobyte plus 256 kilobytes becomes 512 kilobyte of memory, and each chip is a random access memory with output enable, with write enable, with chip select pins. So the total memory is 512 kilobyte. Out of the 20-bit address coming from the microprocessor, 15 pins are connected with each of these chips. So that is represented with this line. So 15 A0 till A15 are connected with the address pins of every memory chip. 16 memory chips are here, divided into 2 groups. And then, okay, so here the buffers are used to just buffer the address coming from the microprocessor. Okay, the next 3 pins, A15, A16, and A17, are used to select either of the inputs from these decoders. So both of all of these 3 inputs are connected with the ABC inputs of these decoders. So both of the decoders are getting the same 3 inputs, and as each of the decoder gets a 3-bit input, would make one of the outputs 0. So one of the output will be 0 here, one of the output will be 0 here, and the next 2 bits are connected to another decoder, and these 2 bits would enable either of these decoder here. So if this decoder is enabled, then either of the chip is selected here, and the 8-bit data is taken from their chip or written to their chip. If these 2 bits select this decoder, and then this would enable this lower bank. So these are kind of 2 banks. So this is one bank, this is another bank. So these 2 bits would choose or enable either of these 2 decoders, which would in turn select a chip inside that particular bank. So this is a bank of memory chips. This is another bank of memory chips. So this bank is providing 256 kilobyte of memory. This bank is providing 256 kilobyte of memory. And this IOM pin is connected through an inverter, and this we would get 0 here. And this is 0 is connected with G1, and 1 is connected with this as IOM prime is here. So a 0 should be provided here, and this would be inverted, and a 1 would be retrieved here. So this 1 is connected with G1 and G1 input of both of these decoders. So when a memory is being accessed, a 0 would be provided here, and this would enable both of these decoders. And when both of these decoders are enabled, the memory read or write operation would happen. And if a 1 is provided here, then that would disable both of these decoders. So a read write operation on the memory would not happen. So this is how 512 kilobytes of random access memory is interfaced with 8088 microprocessor. So these are the 20-bit address. The read write signals are connected with the output enable and the write enable pins of all of these chips. So these control signals would enable either the read operation or the write operation. Similarly, other memory other capacities of memory can also be connected. This is 1 megabyte RAM, 8086 microprocessor with 1 megabyte of random access memory is connected with it. So here in this example, there are 64 kilobytes of chips. So 64 kilo cross 8 memory chip is the 62512. This is the chip ID. So each chip here is 64 kilobytes. So when 64 kilobytes, 8 chips are combined, this would give us 512 kilobyte of memory. And here this is one bank, and when a similar group of chips is combined, another 512 kilobytes of memory would be achieved. So all this together would give us 1 megabyte of total random access memory. So each chip has 8-bit output pins, and as there are 64 kilo locations inside each chip, 16 pins are sufficient to address each location. So out of the 20-bit address, 16 pins, 16 lines, A0 till A15, are connected with every address input of every chip here. So there are 16 total chips, memory chips, each with a capacity of 64 kilobyte, and the 16-bit address is connected with every address input of every chip. And the write and the read commands are control signals are connected with the output enable and the write enable pins of every chip. And then the 3 pins here, A16 till A18, are connected with 2 decoders, and these decoders would choose either one chip in either of the 2 groups, as mentioned for the earlier example. And then there is a bank high enable. This bank high enable would enable the upper bank. If a 0 is provided, then this 0 is connected with G2A, so this bank is enabled, provided if the MIO pin is 1, so that the memory is accessed. This one is connected with G1 and G1 are both of the 2 decoders. So when a memory is to be accessed, then A1 is provided here, so G1 and G1 is 1. And G2B are both decoders are connected with the ground, so this is active low, and 0 is provided. So if bank high enable is 0, then G2A would be selected, and if the bank low enable is 1, then this bank is not selected. So this bank high enable would enable either of the upper bank or the lower bank, and the 16-bit address would identify a location inside either of the chip and either of the bank, and the read signal or the write signal here would identify a read or write operation on either of the memory chip. And so this bank, the output pins of every chip here are connected with the higher 8 bits of the 16-bit data bus, while the lower bank output pins are connected with the low address data pins of the data bus. So from 8086, a 16-bit data bus is coming. So 8 bits, the lower 8 bits are connected with every chip of the output pins in this array, while the upper 8 bits of the data are connected with the output pins of every chip in this upper group of memory chips. And the 16-bit address lines are connected with all of the memory chips here. And these 2 decoders are then used to choose either of the chip in both of these 2 arrays. And the bank high enable may also be used to enable the upper bank if desired, and if this is 1, then the upper bank is not selected and instead the lower bank is selected. There can be a different organization of this 8086 interfacing scheme, whereas the bus low enable, there is no such bank low enable pin in the microprocessor. So this may be connected with in this setup where A0 is also connected, and so through the 2 OR gates. So when bank high enable is 0, A0 is retrieved here, so the upper bank is selected. And when A0 is 0, the lower bank is also selected. And when both are zeros, this is 0, this is 0, then both of the banks are selected. And when both are 1, then none of the banks is selected. So this is a very simple example of interfacing 8086 microprocessor with the 1 megabyte of random access memory.